Hello there, and welcome back to this quiet space where questions linger and curiosity doesn't need to rush. Tonight, we're going to explore something so familiar that you might never have stopped to wonder about it. Something so obvious that it hides in plain sight every time you step into a shower, every time you watch rain fall, every time you stand at the edge of the ocean and feel the spray on your face. We're going to ask a question that seems almost too simple, yet opens into depths that stretch back hundreds of millions of years. Why can't we breathe underwater? And before you think the answer is obvious, consider this. Water, the substance that covers more than 70% of our planet's surface, the liquid that fills our oceans and rivers and lakes, the compound we drink and bathe in and cannot live without, is made of oxygen. 2 atoms of hydrogen bonded to 1 atom of oxygen, H2O. The very element our lungs crave, the gas our cells burn for energy, the molecule without, which we die in minutes, is right there, locked inside every drop. Yet if you were to sink beneath the surface, if you were to open your mouth and let that water pour into your lungs, you would not breathe. You would drown. This is the paradox we're stepping into tonight. A world where fish glide through the depths, pulling life from the same water that would kill us, where oxygen exists all around, yet remains just out of reach. And the answer to why this happens, why we're built the way we are, takes us into the deep machinery of chemistry and evolution, into a story written in the structure of molecules and the architecture of organs that took hundreds of millions of years to shape. Before we begin that journey, settle in. Maybe you're listening late at night, when the house is quiet and the world has slowed down. Maybe you're looking for something to occupy your mind while it drifts towards sleep. Either way, there's no rush. This story has been unfolding for longer than our species has existed, and it will continue long after we're gone. The water isn't going anywhere. The question isn't going anywhere. So let's take our time with it. Let's walk through it slowly, carefully, the way you might wade into a cool lake on a summer evening, one step at a time, feeling the temperature change against your skin, noticing how your body reacts to something as simple as being surrounded by water. Because that's where the mystery starts. With that first breath you can't take, with that first moment when your body realizes it's in an element it wasn't designed for. Think about what happens when you go underwater. Not for long, just for a moment. You take a breath first, filling your lungs with air, and then you sink below the surface. And for a little while everything is different. Sound changes, becoming muffled and strange, as if the world has been wrapped in cotton. Light bends and refracts, making distances harder to judge, colours shifting toward blue and green. Gravity feels softer, gentler, as the water buoys you up and you float with an ease impossible on land. Your hair floats upward, swaying with currents you can't quite see. Bubbles rise past your face, each one catching the light as it spirals toward the surface. There's something peaceful about it, something almost meditative, as long as you don't think too hard about what's happening inside your body. But the most immediate thing, the thing you notice within seconds, is the pressure in your chest, the need to breathe. It starts as a whisper, a gentle suggestion that you might want to head back up soon. Then it grows louder, more insistent, transforming from a suggestion to a demand. Your diaphragm starts to spasm slightly. Your throat tightens. Carbon dioxide is building up in your blood, and sensors in your brainstem are picking up on it, sending increasingly urgent signals that it's time, it's past time, you need to breathe now. And still you might hold on a few seconds longer, testing yourself, seeing how far you can push. But eventually, inevitably, the urge becomes overwhelming. It's the only thing you can think about. Your vision might start to narrow at the edges, your chest might ache, and when you finally surface, when you break through that barrier between water and air and gasp that first breath, your whole body floods with relief. The oxygen hits your bloodstream, the carbon dioxide escapes. Everything in you says yes, this is right. This is what we needed. That moment, that desperate pull toward air and the overwhelming relief when you get it, is your body telling you a truth that goes deeper than thought. You're not built for this. You cannot stay here. You are made for air, for the surface, for the world above. And yet, in that same water, perhaps just a few meters away, fish are breathing just fine, not holding their breath the way you are, not counting the seconds until they can surface, actually breathing, pulling oxygen from the water that surrounds them, living their entire lives submerged in what would be your grave. A trout might swim past, its gills rhythmically opening and closing, water flowing in through its mouth and out through the gill slits, in a constant, easy cycle. It's not struggling. It's not thinking about breathing any more than you think about breathing when you're walking down the street. For the fish, water is air. It's the medium of life, the thing it breathes as naturally as you breathe the atmosphere. So what's the difference? What do they have that we don't? And more importantly, why don't we have it? Why did evolution give fish one solution and us another? And what would it take to change that? The answer begins with chemistry, with the most basic building blocks of matter. Water is not a simple thing. It seems simple when you pour it from a glass or feel it run through your fingers, but at the molecular level it's a tightly bound structure. Each water molecule, that familiar H2O, consists of 2 hydrogen atoms covalently bonded to 1 oxygen atom. And those bonds, those connections between atoms, are strong. They require energy to break, far more energy than the simple act of breathing can provide. When you breathe air, you're not breaking anything apart. You're not pulling oxygen away from other elements or tearing molecules in half. The oxygen in air exists as O2, 2 oxygen atoms bonded together, floating freely as a gas. Your lungs don't have to do any chemical work. They just need to absorb what's already there, ready and waiting to diffuse across the thin membranes of your alveoli and into your bloodstream. It's a passive process, driven by concentration gradients, by the simple fact that there's more oxygen in the air you inhale than in the blood flowing through your lungs. So the oxygen moves from where there's more to where there's less, the way heat flows from hot to cold or water flows downhill. But in water, the oxygen you need isn't free, it's locked up. The oxygen atom in H2O is bound to those hydrogen atoms so tightly that your body has no mechanism to break it free. Your lungs can't pull hydrogen and oxygen apart. They can't perform the chemical reaction that would be needed to liberate that oxygen and make it usable. That would require energy, specialized enzymes, processes your respiratory system simply doesn't have. And even if it did, the byproduct would be hydrogen gas, which your body also has no use for and no good way to expel. The whole system would be a disaster. So the oxygen in water molecules, the oxygen that makes up the very structure of water itself, might as well not exist as far as your lungs are concerned. It's there, but it's invisible to you, inaccessible, locked away behind chemical bonds you cannot break. Now, there is oxygen in water that fish can use, but it's not the oxygen in the water molecules themselves, it's dissolved oxygen. Atmospheric oxygen, the same O2 you breathe, can dissolve into water the way carbon dioxide dissolves into a soft drink or the way sugar dissolves into tea. When air meets water at the surface, some of that oxygen crosses the boundary and disperses into the liquid, floating between the water molecules, still existing as free O2 but now suspended in a liquid medium instead of a gaseous one. And fish breathe that dissolved oxygen, not the water. They're not breaking apart H2O any more than you are. They're extracting the free oxygen that happens to be present in the water around them. But here's the problem, the fundamental challenge that makes underwater breathing so difficult. Water holds far, far less oxygen than air does. In a litre of fresh water at room temperature, there might be about 8 millilitres of dissolved oxygen. In that same volume of air, there would be about 210 millilitres of oxygen. Air has roughly 26 times more oxygen than water, volume for volume, and that's not even accounting for how much harder it is to move water than air. Water is dense, it's heavy. It takes work to push it through gills or any other breathing apparatus. It's 800 times denser than air and about 100 times more viscous. Imagine trying to breathe soup instead of air, and you start to get a sense of the physical challenge involved. So fish face a problem we don't. They live in a medium where oxygen is scarce and expensive to extract. Every breath a fish takes requires effort. It has to pull water in through its mouth, force it over its gills, and push it back out through the gill openings, and all of that just to capture the tiny amount of dissolved oxygen present in that water. It's a constant process, never-ending, as essential and automatic as your own breathing, but far more demanding in terms of the work involved. And because there's so little oxygen to work with, fish have evolved one of the most efficient respiratory systems in the animal kingdom. Their gills are marvels of biological engineering, structures built to extract every last molecule of usable oxygen from the water passing over them. If you could see a gill up close, magnified and slowed down, you'd find yourself looking at something that seems almost impossibly delicate. Imagine a comb, but one made of living tissue, blood red and constantly moving. The main structure, the gill arch, is a curved support made of bone or cartilage, and attached to it are rows upon rows of thin filaments, each one lined with even thinner plates called lamellae. These lamellae, sometimes called secondary lamellae to distinguish them from the filaments themselves, are where the magic happens. Each one is incredibly thin, sometimes just a few cells thick, and each is filled with tiny blood vessels, capillaries so close to the surface that only a gossamer membrane separates the blood from the water flowing past. This membrane is the boundary between life and death for the fish. Oxygen diffuses across it, moving from the water into the blood, while carbon dioxide moves the other direction, from the blood into the water, to be carried away and expelled through the gill openings. The total surface area created by all these filaments and lamellae is enormous. A fish might have 4 or 5 gill arches on each side of its head, and each arch supports hundreds of filaments, and each filament is covered in dozens or hundreds of lamellae. All told, the surface area available for gas exchange in a fish's gills can exceed the surface area of its entire body. That's an extraordinary adaptation, packing that much functional tissue into the small space behind the gill covers. It's as if you could fold a tennis court into something the size of a shoebox. And all of it is perfused with blood. All of it is actively exchanging gases all the time as long as water keeps flowing. But surface area alone isn't what makes gills so efficient. Plenty of structures have large surface areas. What matters is how that surface area is used. And in fish, the key is in the way water and blood move past each other. In most animals that breathe air, including us, the breathing medium, air, and the transport medium, blood, interact in what's called a concurrent flow system, or sometimes a tidal system. Air comes into the lungs, fills them up, exchanges gases with the blood, and then flows back out the same way it came in. The blood and air meet, exchange gases, and part ways. It's simple, and it works reasonably well when oxygen is abundant. But fish can't afford to be wasteful. They can't leave oxygen behind because there isn't enough of it to spare. So they use a different system, one that maximizes extraction efficiency. It's called countercurrent exchange. In a countercurrent system, the water flowing over the gills and the blood flowing through the capillaries inside the gills move in opposite directions. The water enters the fish's mouth, passes over the gills from front to back, and exits through the gill openings. Meanwhile, the blood enters the gill filaments from the back and flows toward the front, exactly opposite to the water flow. And this arrangement, simple as it sounds, changes everything. Because at every point along the gill filament, the blood is meeting water that has slightly more oxygen than the blood does. Even when the blood is nearly saturated with oxygen, when it's picked up almost all it can carry, it's still encountering water that has just a little bit more. Fresh water that's just arriving and hasn't given up its oxygen yet. So oxygen keeps diffusing across the membrane, keeps moving from water to blood, all the way down the length of the gill. The gradient is maintained, the driving force for diffusion never disappears, and as a result, fish can extract up to 80 or even 85% of the oxygen present in the water they breathe. To put that in perspective, your lungs, breathing air, extract only about 25% of the available oxygen. Most of the oxygen in the air you inhale gets exhaled right back out, unused. That's fine when oxygen is abundant, when there's plenty to go around. You can afford to be inefficient, but fish can't. They're extracting from a medium that's already oxygen poor, and they're pulling out 4 times as much of what's available as you do from air. It's one of nature's most elegant solutions to a difficult problem, and it only works because of that countercurrent flow. If fish gills worked like mammal lungs, if water and blood flowed in the same direction, they'd extract maybe 30 or 40% of the oxygen, and that wouldn't be enough. They'd suffocate even while breathing. The countercurrent system is what makes aquatic life possible for creatures with high metabolic demands. And yet, for all their brilliance, gills wouldn't work for us. Not just because we don't have them, though that's true enough, but because the physics of being a mammal makes gills impractical even if we could somehow grow them. Fish are cold-blooded. Their body temperature matches the water around them, which means their metabolism runs slowly compared to ours. They don't need as much oxygen per unit of body mass, because they're not burning as much energy to maintain a constant internal temperature. We are warm-blooded. We burn fuel constantly to keep our bodies at around 98.6 degrees Fahrenheit, no matter what the temperature is outside. That takes energy, lots of it, and energy requires oxygen. Our oxygen demands are far higher than a fish's. Even the most efficient gills, extracting 80% of the oxygen in water, wouldn't be able to supply enough to keep a warm-blooded mammal alive. This is why whales and dolphins and seals, all warm-blooded mammals that spend their lives in the ocean, don't have gills. They breathe air. They come to the surface, fill their lungs, and hold their breath while they dive. It's the only way their metabolism can get enough oxygen to function. Our lungs, meanwhile, are built for a completely different task. If gills are fishing nets designed to catch oxygen from water, lungs are sponges designed to soak it up from air. The architecture is different. The physics is different. The whole system works on assumptions that simply don't apply underwater. When you inhale, air travels down your trachea, your windpipe, and into your bronchi, the two main branches that lead into your left and right lungs. From there, the bronchi split again and again, dividing into smaller and smaller airways called bronchioles, like a tree branching into twigs, and then into the finest possible branches. At the end of these tiniest airways sit clusters of microscopic sacs called alveoli. You have roughly 300 million of them. Each one is incredibly thin-walled, just a single cell thick in places, surrounded by a mesh of capillaries, blood vessels so small that red blood cells have to squeeze through them one at a time. When oxygen-rich air fills an alveolus, oxygen diffuses across that thin wall into the capillaries, binds to hemoglobin in the red blood cells, and gets carried off to wherever your body needs it. Carbon dioxide does the reverse, moving from the blood into the alveoli to be exhaled. It's elegant, it's efficient, and it only works with air. The surface area of all those alveoli combined is astonishing. If you could somehow unfold your lungs and spread them flat, they'd cover somewhere between 70 and 100 square meters, about the size of a tennis court, all of that packed into the space of your chest. That enormous surface area allows your lungs to absorb oxygen quickly from the air you breathe. But air is light. It's thin. It moves easily. You can pull it into your lungs and push it back out without much effort. Water, on the other hand, is heavy, dense. Trying to pull water into your lungs would be like trying to inhale mud. The effort alone would exhaust you, but even if you somehow managed it, even if you filled your lungs with water, the oxygen transfer still wouldn't work. The lining of your alveoli is adapted to handle air, not liquid. It's coated with a thin layer of fluid that helps oxygen dissolve and cross into your bloodstream, but that fluid is meant to interact with gases, not to be flooded with liters of water. And remember, water holds far less oxygen than air. Even if your lungs could somehow extract dissolved oxygen from water, which they can't do efficiently, the concentration is so low that you'd need to move enormous volumes of water through your lungs just to get a fraction of the oxygen you'd get from a single breath of air. Your respiratory muscles couldn't handle it. The work of breathing would consume more oxygen than you'd be gaining. You'd suffocate even as your lungs filled and emptied. There's another problem too, one that comes down to simple physics. Water is incompressible. It doesn't squeeze down the way air does. When you dive, underwater, the pressure around you increases. For every 10 meters you descend, the pressure goes up by roughly 1 atmosphere. At 10 meters deep, the pressure is twice what it is at the surface. At 20 meters, it's 3 times. And as pressure increases, the air in your lungs compresses, getting smaller and denser. Your body is built to handle this to some extent. Your ribcage can flex, your diaphragm can adjust, but if your lungs were full of water, there'd be no give. Water doesn't compress. The pressure would bear down on your chest with nothing to cushion it, and your lungs, those delicate structures designed to expand and contract with air, would be crushed. Divers who go deep enough without equalizing the pressure in their lungs can experience lung squeeze, a painful and dangerous condition where the lungs collapse inward under the weight of the surrounding water. Imagine what would happen if your lungs were filled with water to begin with. There would be no air pocket to compress, no cushion to absorb the pressure, just the rigid, unyielding weight of liquid pressing against tissue that wasn't built to bear it. And yet, for all these reasons why we can't breathe underwater, the story isn't quite as simple as lungs versus gills, because we didn't always have lungs. Or rather, our very distant ancestors, the fish that eventually gave rise to all land-dwelling vertebrates, had both, gills and lungs. This might sound strange, but it's true. Lungs are ancient. They appeared in fish long before the first creatures crawled onto land, long before there were tetrapods or amphibians or anything resembling a mammal. Somewhere around 400 million years ago, certain groups of fish living in freshwater environments began developing lungs as a way to supplement their gills. These weren't lungs like ours, not at first, but simple sacs that could hold air, allowing the fish to gulp oxygen from the surface when the water around them became stagnant or oxygen poor. In swamps and shallow ponds where oxygen levels could drop dangerously low, having lungs was a survival advantage. It meant you didn't have to rely entirely on dissolved oxygen in the water. You could breathe air when you needed to, giving yourself a backup option when conditions got tough. These early lunged fish, the ancestors of both modern lungfish and the entire lineage of tetrapods that includes us, lived in a world very different from today. The Devonian period, sometimes called the Age of Fishes, was a time of experimentation and diversification. Plants had colonized the land, but animals were still largely aquatic. The continents were configured differently. Climates fluctuated, and in the shallow waters of ancient rivers and lakes, fish were evolving all sorts of adaptations to cope with changing conditions. Some developed bony structures in their fins that would eventually become the bones of arms and legs. Some developed necks, allowing their heads to move, independently of their bodies, and some developed lungs. At first, those lungs were just one option among many. Fish with lungs still had gills. They used both. They were amphibious in a way, capable of extracting oxygen from water or air depending on what was available. But over millions of years, as some of these fish began spending more time in shallow water, as they began venturing onto mudflats and riverbanks, as they slowly transitioned from aquatic life to a more terrestrial existence, the balance shifted. Lungs became more important. Gills became less so. The fossil record shows us the steps along this journey, though it's incomplete and full of gaps. We have Tiktaalik, a creature that lived about 375 million years ago, with features of both fish and tetrapods. It had gills, but it also had lungs. It had fins, but those fins had bones inside them that look remarkably like the bones in your arm. It had a neck, something fish don't have, that allowed it to lift its head and look around. It probably spent time in shallow water, pushing itself along the bottom with those muscular fins, perhaps even hauling itself onto land for short periods, and it breathed air. Not exclusively, but enough that its lungs were functional, useful, essential to its survival. Creatures like Tiktaalik were the bridge between two worlds. They hadn't fully committed to land yet, but they were moving in that direction. And with each generation, with each small change in anatomy and physiology, their descendants became a little more terrestrial and a little less aquatic. By the time the first true tetrapods appeared, fully limbed animals that could walk on land even if they still depended on water for reproduction, lungs had become the primary respiratory organ. Gills were gone or nearly gone, reduced to vestiges that appeared briefly during development and then vanished. The shift was complete, or nearly so, because even today in the bodies of modern mammals, including humans, you can still see traces of our aquatic past. When a human embryo develops in the womb, it goes through stages that echo that ancient transition. At about 4 weeks of development, structures called pharyngeal arches appear in the neck region of the embryo. In fish, these arches develop into gills. In humans, they don't. They transform into other things: the jaw, the inner ear bones, parts of the throat and larynx. But for a brief window of time, the embryo carries the blueprint for gills, a ghostly reminder of the fish we used to be. It's written into our DNA. Not functional gills, not anything that would allow us to breathe underwater, but the pattern is there, the ancient code that once built gills in our ancestors. And our lungs, the organs we use every moment of our lives, are themselves modified swim bladders, structures that fish use to control buoyancy. Swim bladders and lungs share a common origin. Both are outpouchings of the digestive tract. Both are filled with gas. But in fish, the swim bladder became a flotation device, helping the fish maintain its position in the water column without having to constantly swim. In the lineage that led to land animals, the swim bladder became a lung, a gas exchange organ that allowed breathing in air. It's the same structure, repurposed. Evolution doesn't build from scratch. It tinkers with what's already there, modifying and reshaping until something new emerges. And what emerged, in the ancestors of all land vertebrates, was a respiratory system built for air, optimized for air, dependent on air. When those early tetrapods left the water for good, when they committed fully to life on land, they gave up the ability to breathe underwater. It wasn't a loss they mourned, obviously. It was a trade. Gills for lungs. water for air. And it worked. It worked so well that their descendants, all of us, every mammal and bird and reptile that walks or flies or climbs or burrows, have inherited that choice. We breathe air. That's what we do. That's what we're built for. And going back underwater, trying to reclaim that lost ability, isn't just difficult. It's impossible without changing the fundamental architecture of our bodies. But even though we can't breathe underwater, we haven't entirely lost our connection to the water. Buried in our physiology, deeper than conscious thought, is a response that kicks in whenever we submerge. It's called the mammalian diving reflex, and it's a reminder that we're not as far removed from the ocean as we might think. When you hold your breath and put your face in cold water, your body does something automatic, something you don't control and probably don't even notice unless you're paying attention. Your heart rate slows, not a little. It can drop by 10 to 30%, sometimes even more in trained divers. At the same time, blood vessels in your extremities, in your arms and legs and hands and feet, constrict, narrowing down to reduce blood flow to those regions. Your body is redistributing its resources, redirecting blood toward your core, toward your heart and brain and lungs. These are the organs that need oxygen the most, the ones you can't afford to lose, and your body knows it. Without any conscious input from you, without you deciding anything, your circulatory system reorganizes itself, prioritizing survival. This is the diving reflex, and it's not unique to humans. All mammals have it. Seals and whales and otters and dolphins have it far more strongly developed than we do, because they spend their lives in the water and need every advantage they can get to stay underwater for extended periods. A Weddell seal, hunting beneath Antarctic ice, can dive for 40 minutes or more on a single breath. During that time, its heart rate drops from around 100 beats per minute down to 10, sometimes as low as 5. Its peripheral blood vessels clamp down almost completely, shutting off flow to the blubber, the skin, the flippers, everything except the absolutely essential core organs. The muscles in its body switch to anaerobic metabolism, burning fuel without oxygen and building up lactic acid that will have to be cleared later when the seal surfaces. It's an extraordinary adaptation, allowing an animal to stay underwater far longer than its oxygen supply would normally allow. The seal is essentially rationing its oxygen, using it as sparingly as possible, stretching every breath to its absolute limit. Sperm whales take this even further. They can dive to depths exceeding 2,000 meters, staying down for 90 minutes or more, hunting giant squid in the absolute darkness of the deep ocean. Their bodies are adapted in ways ours are not. They have proportionally larger lungs. Their blood carries far more hemoglobin, the protein that binds oxygen, than ours does. Their muscles are packed with myoglobin, another oxygen-binding protein that stores oxygen in the tissue itself, giving the muscles a dark red, almost maroon colour. They have collapsible rib cages that allow their lungs to compress under pressure without being damaged. They have special adaptations in their blood vessels, networks of small vessels called rite wonderful nets that help conserve heat and protect against nitrogen narcosis. Every system in their body is tuned for one purpose: to maximize the time they can spend in the lightless depths, far from air. And at the center of it all is the diving reflex, the same basic mechanism we have, amplified and refined over millions of years of evolution. But we have it too. It's ancient. It's hardwired. Researchers studying the diving reflex in humans have found that even newborn infants display it. If you immerse a baby's face in water, carefully, just for a moment, their heart rate will drop and their breathing will pause. It's instinctive, a protective mechanism that prevents the baby from inhaling water. Over time, as the child grows, the reflex doesn't disappear, but it becomes less pronounced, requiring both facial immersion and breath holding to fully activate. By adulthood, you need cold water on your face, and you need to be holding your breath for the full effect to kick in. But it's still there. The same reflex that helps a seal dive beneath the ice is present in you, waiting, ready to activate the moment your face touches cold water and your breathing stops. Freedivers, people who train to hold their breath and dive deep without any equipment, learn to enhance this reflex through practice and conditioning. They spend hours, days, years training their bodies to tolerate low oxygen levels, to relax into the discomfort of breath holding, to let the diving reflex do its work without fighting it. Some of them can hold their breath for more than 10 minutes while floating motionless in a pool. Some can dive below 100 meters, even 150 meters, on a single breath, descending into darkness where the pressure is crushing and the cold intense, and then returning to the surface, alive and conscious and ready to do it again. These are extraordinary feats, pushing the human body to its absolute limits, and they're only possible because of the diving reflex and the physiological changes it triggers. It buys them time, it stretches out the oxygen in their blood, making each breath last longer than it normally would. It keeps their brains alive when by all rights they should be unconscious. There are even populations of humans who have, over generations, developed enhanced diving responses. The Bajau people of Southeast Asia, sometimes called sea nomads, spend much of their lives in the water, diving for fish and shellfish, and research has shown that they have larger spleens than typical humans. The spleen acts as a reservoir for red blood cells, and during a dive it contracts, releasing those stored cells into the bloodstream and temporarily increasing the blood's oxygen-carrying capacity. It's a form of biological blood doping, and the Bajau have, through centuries of natural selection, developed spleens that are 50% larger than average. Similarly, the Haenyeo women divers of Jeju Island in South Korea, who have been free diving for shellfish for generations, show remarkable cold tolerance and cardiovascular adaptations. Their bodies have become fine-tuned to the demands of repeated breath-hold diving in a way most humans' bodies are not. They're not breathing underwater, they're not exempt from the limitations we all share, but they're pushing those limitations further than most people thought possible. But even the diving reflex doesn't let us breathe underwater, it just delays the inevitable. You're still holding your breath. You're still using up the oxygen you brought with you from the surface. Eventually that oxygen runs out. Carbon dioxide builds up in your blood, your body starts screaming at you to breathe, and if you don't surface, if you don't get back to air, you'll pass out and drown. The reflex can extend your time underwater, but it can't give you gills. It can't extract oxygen from the water around you. You're still dependent on the air you took in before you went under. And there's a limit to how much air your lungs can hold, how long your blood can sustain your brain, how far you can push before your body shuts down. The ocean is patient. It doesn't care how well trained you are. It doesn't care about your reflex. If you stay too long, it will take you. There have been experiments, strange and ambitious attempts to find ways around this limitation. Scientists have developed something called liquid breathing, where instead of breathing air, a person breathes a special fluid. Perfluorocarbons, synthetic liquids that can dissolve far more oxygen and carbon dioxide than water can. The idea is that if you fill your lungs with this oxygen-rich liquid, you might be able to extract enough oxygen to survive, bypassing the need for air entirely. It sounds like science fiction, and in many ways it still is. Experiments with liquid breathing have been conducted on animals and, in a few rare cases, on humans in medical settings. Premature babies with damaged lungs have been treated with partial liquid ventilation, where a perfluorocarbon liquid is instilled into the lungs to help them function more effectively. The results have been mixed. The liquid does carry oxygen. The lungs can absorb some of it. But there are problems, big ones. Breathing liquid is hard, really hard. Your respiratory muscles aren't designed to move dense fluid in and out of your lungs. The effort is exhausting, and even with the most oxygen-rich perfluorocarbons, the amount of oxygen you can extract still isn't enough to sustain a person for long. You'd need mechanical assistance, pumps to circulate the fluid, systems to refresh the oxygen content. It's not practical for diving, it's not practical for anything outside a hospital, really. And even if it were, even if we could somehow engineer a system that worked, you still wouldn't be breathing water. You'd be breathing a synthetic fluid engineered to do what water cannot. Water itself, ordinary H2O, will never work. The density is too high. The oxygen content is too low. The physical demands are too great. You cannot breathe it. You cannot survive in it. And no amount of training or technology or genetic engineering, short of completely rebuilding your respiratory system from the ground up, will change that. We are land animals. We evolved lungs for a reason, and that reason was to leave the water behind. To walk on solid ground, to breathe the open air, to claim a new niche, a new way of living that the ocean could never offer. And in doing so, we gave up something. We gave up the ability to live submerged. We traded one world for another. And there's no going back without losing everything we've become. Yet for all that, water still calls to us. We're drawn to it in ways that feel almost primal. We build our cities near coastlines. We vacation at the beach. We swim for pleasure even though swimming is harder. less natural for us than walking. We dive, we surf, we sail. We're fascinated by the ocean, by what lives in it, by what mysteries it holds. And maybe that fascination is a kind of memory, not a conscious one, but something deeper, a recognition buried in our cells that we came from there, that the first stirrings of life on this planet happened in the water, that every living thing, including us, traces its lineage back to the ocean. We carry seawater in our veins. The salt content of our blood is remarkably close to the salt content of the ocean, a similarity that's not coincidence but inheritance. Our earliest ancestors were marine creatures, and even after billions of years of evolution, even after we crawled onto land and grew lungs and became mammals and eventually humans, we still carry that signature. We're still, in a sense, the ocean's children. And maybe that's why it feels so strange, so paradoxical that we can't breathe in it. It's like being locked out of your childhood home. You remember it, you know it was yours, but the door is closed and you can't get back in. The truth is, we're caught between two worlds. We need water to survive. We're made mostly of water. About 60% of your body weight is water. Your brain is 73% water. Your lungs are 83% water. You can survive weeks without food, but only days without water. It's essential to every process in your body, every chemical reaction, every cell function. And yet the moment you submerge in it, the moment it surrounds you completely, it becomes a threat, a danger. The thing you need most becomes the thing that can kill you fastest. It's a contradiction we live with every day without really thinking about it. We drink water, we bathe in it, we use it to cook, to clean, to cool ourselves down on hot days, but we don't breathe it. We can't. And when we find ourselves underwater, when we're swimming or diving or, in the worst cases, drowning, our bodies react with everything they have to keep that water out of our lungs. We cough, we gag, our airways close involuntarily. The larynx spasms sealing off the trachea, preventing even a drop of water from getting through. This is called laryngospasm, and it's a reflex so powerful it can keep water out of your lungs even when you're unconscious. Even when you're drowning, your body fights to protect your airways because it knows, at a level deeper than thought, that water in the lungs means death. And when water does get in, when the laryngospasm fails or is overwhelmed, when water floods into the alveoli and fills those delicate air sacs, breathing stops. Oxygen can't cross into your bloodstream. Carbon dioxide can't get out. Your blood becomes acidic. Your brain, starved of oxygen, begins to shut down. Within minutes, if you're not rescued, you die. Not from water itself necessarily, but from the lack of oxygen, from asphyxiation. The water is just the medium, the thing that prevents air from reaching your lungs. It's not toxic. It's not poisonous. It's just wrong. Wrong for your lungs. Wrong for the way your body extracts oxygen. Wrong for a creature that evolved to breathe air. So we come back to where we started, to the question that seemed so simple and turned out to be anything but. Why can't we breathe underwater? Because we're not built for it. Because our lungs evolved for air, not water. Because the oxygen in H2O is locked away behind chemical bonds we can't break, and the dissolved oxygen in water is too sparse, too dilute, too hard to extract for a warm-blooded mammal with high oxygen demands. Because our ancestors, 400 million years ago, made a choice. They developed lungs. They ventured onto land. They gave up gills, and we inherited the consequences of that choice. We inherited lungs that work beautifully in air and fail completely in water. We inherited a respiratory system optimized for one environment and helpless in another. And we inherited a body that still remembers the ocean, still responds to submersion with reflexes that go back millions of years, but can no longer live there. It's humbling in a way, to realize how specific our adaptations are, how finely tuned to one narrow set of conditions. We think of ourselves as adaptable, as masters of our environment, and in many ways we are. We've spread to every continent. We live in deserts and tundras and jungles and mountains. We've built cities in places that should be uninhabitable and found ways to survive in conditions that would kill us without technology. But we can't breathe underwater. That's beyond us. It always will be, unless we change what we are so fundamentally that we'd no longer be human. And maybe that's okay. Maybe it's a reminder that for all our intelligence and tool-making and ability to reshape the world around us, we're still animals, still shaped by evolution, still carrying the marks of a history that stretches back further than we can imagine, still bound by limits we didn't choose and can't escape. The ocean will always be there, vast and deep and full of life we can barely comprehend, and will always be visitors to it. Brief guests. We can wade in its shallows, we can swim on its surface, we can dive beneath it for moments, holding our breath, stealing time. But we can't stay. We have to come back to the air, back to the world we were made for. And maybe, in the end, that's enough. To know where we came from, to understand why we're built the way we are, to appreciate the long, slow journey from water to land, from gills to lungs, from fish to mammals to us. We don't need to breathe underwater to be connected to the ocean. We carry that connection inside us, in our blood, in our cells, in the reflexes that trigger when we submerge. The ocean shaped us, gave us life, let us go. And we remember. In our bodies, in our biology, in the quiet way our hearts slow when our faces touch cold water, we remember. But even the diving reflex doesn't let us breathe underwater. It just delays the inevitable. You're still holding your breath. You're still using up the oxygen you brought with you from the surface. Eventually that oxygen runs out. Carbon dioxide builds up in your blood. Your body starts screaming at you to breathe. And understanding why that urge becomes so overwhelming, why you can't simply ignore it and stay underwater longer, takes us into one of the most fascinating aspects of how breathing actually works. You might think that the urge to breathe comes from running out of oxygen, that when your blood oxygen drops too low, your brain detects it and forces you to gasp for air. But that's not quite how it works. The primary driver of breathing, the thing that makes you feel desperate for air when you hold your breath, isn't low oxygen, it's high carbon dioxide. Your body is far more sensitive to carbon dioxide levels than to oxygen levels. This might seem backward, but it makes sense when you think about how breathing actually functions. Under normal circumstances, oxygen levels in your blood stay relatively high and stable. Your lungs are efficient enough that each breath brings in more than enough oxygen to keep your blood well saturated. The real problem is getting rid of carbon dioxide, the waste product of metabolism. Every cell in your body is constantly burning fuel to produce energy, and carbon dioxide is the exhaust from that process. It diffuses out of your cells into your blood, where it's carried to your lungs to be exhaled. If carbon dioxide builds up, it doesn't just sit there harmlessly. It reacts with water in your blood to form carbonic acid, which breaks down into hydrogen ions. And those hydrogen ions make your blood more acidic, lowering its pH. Your body is exquisitely sensitive to changes in blood pH. Even small shifts can disrupt enzyme function, protein structure, and all sorts of biochemical processes that keep you alive. So your brainstem, the part of your brain that controls breathing without any conscious input from you, is constantly monitoring carbon dioxide levels. Not directly, but indirectly, by detecting pH changes in your blood and in the fluid surrounding your brain. There are two sets of sensors involved in this monitoring. Central chemoreceptors, located on the surface of the medulla in your brainstem, detect changes in the pH of cerebrospinal fluid, which mirrors changes in blood carbon dioxide. Peripheral chemoreceptors, located in the carotid bodies in your neck and the aortic bodies near your heart, detect changes in blood oxygen, carbon dioxide and pH directly. But it's the central chemoreceptors, responding to carbon dioxide and pH, that do most of the heavy lifting under normal conditions. When carbon dioxide levels rise, when pH drops, these sensors fire signals to the respiratory center in your brainstem, which increases the rate and depth of your breathing. More breaths, deeper breaths, more carbon dioxide expelled. The system is a negative feedback loop, constantly adjusting to keep carbon dioxide and pH within a narrow, healthy range. This is why holding your breath becomes so uncomfortable so quickly. Within seconds, carbon dioxide starts accumulating in your blood. The pH starts to drop. The chemoreceptors start firing. Your diaphragm begins to spasm involuntarily, trying to force you to breathe. The longer you hold your breath, the stronger the urge becomes, until it's overwhelming, irresistible, a screaming demand from your brainstem that you must breathe right now. And if you're underwater when that happens, if you can't get to the surface in time, your body will eventually override your conscious control. You'll gasp, you'll inhale, and if you're still submerged, you'll inhale water. This is how drowning begins. The process of drowning is not what most people imagine. It's not a peaceful drift into unconsciousness. It's not gentle. It's a panic, a fight, a series of physiological responses that your body goes through as it tries desperately to survive. When someone first goes under, their instinct is to hold their breath. They're struggling to keep their head above water, to get air, but eventually exhaustion or injury or some other factor causes them to slip beneath the surface, and once they're under, unable to breathe, the breath holding begins. How long they can hold their breath depends on many factors: water temperature, physical fitness, how much they've been struggling, how much oxygen they had in their lungs to begin with. In warm water, a person might hold their breath for 30 seconds, maybe a minute. In cold water, the cold shock response, the sudden gasping reflex that happens when you hit cold water, can cut that time down to just seconds. Eventually, carbon dioxide builds up enough that the urge to breathe becomes unbearable. The diaphragm spasms. The person might try to swim for the surface, but if they can't make it, if they're too deep or too disoriented or too weak, they'll reach their breaking point. And when they do, they'll gasp. They'll involuntarily try to inhale, and water will enter their mouth and throat. At this point, one of two things happens. In most cases, the water touching the back of the throat triggers a reflex called laryngospasm. The vocal cords snap shut, sealing off the airway, preventing water from entering the lungs. It's a protective reflex meant to keep foreign matter out of the respiratory system. But while it's protecting the lungs, it's also preventing breathing. The person can't get air. Carbon dioxide continues to build. Oxygen continues to drop. The laryngospasm might last 10 seconds, 20 seconds longer. During that time, the person is effectively suffocating. In about 10 to 15% of drowning cases, the laryngospasm persists until the person loses consciousness and their heart stops. This is sometimes called dry drowning, though the term is misleading and not really used in modern medical practice anymore. The lungs stay relatively dry because the spasm kept the water out. But the person still drowns, still dies from lack of oxygen because they couldn't breathe. In the remaining 85 to 90% of cases, the laryngospasm eventually relaxes, usually as oxygen levels drop and the person begins to lose consciousness. When it does, water rushes into the lungs. The person might cough, might gag, but they're taking in more water with each involuntary breath. Water floods into the bronchi, into the smaller airways, into the alveoli. And once water reaches the alveoli, the damage begins immediately. Remember that the alveoli are designed for air. They're lined with a substance called surfactant, a mixture of lipids and proteins that reduces surface tension and keeps the alveoli from collapsing when you exhale. Water, whether it's fresh water from a lake or salt water from the ocean, disrupts that surfactant. Fresh water, being hypertonic, dilutes it. Salt water, being hypertonic, draws fluid out of the blood vessels and into the alveolar space, washing the surfactant away. Either way, the result is the same. The alveoli lose their ability to function properly. They become unstable, prone to collapsing. The delicate membranes between air and blood become inflamed, swollen. Fluid leaks from the capillaries into the alveolar spaces, creating pulmonary edema, the lungs filling with the body's own fluids in response to the injury. Gas exchange becomes impossible. Oxygen can't cross into the blood. Carbon dioxide can't get out. The blood becomes more and more acidic, more and more depleted of oxygen, and without oxygen, the brain starts to shut down. Within minutes, brain cells begin to die. The heart, starved of oxygen, develops arrhythmias, irregular beating patterns, and eventually stops altogether. This is drowning. This is what happens when water enters lungs that were never meant to hold it. It's not just the water itself that kills, though the water is certainly the trigger. It's the cascade of physiological failures that follows, the breakdown of all the systems that depend on breathing to function. And yet, remarkably, some people survive. If they're pulled from the water quickly enough, if resuscitation begins immediately, if their heart can be restarted and their lungs cleared and supported, some people come back. The human body is resilient in ways that can seem almost miraculous. Even after the heart has stopped, even after breathing has ceased, if the brain hasn't been without oxygen for too long, recovery is possible. But it's a narrow window. Brain cells start dying after about 4 to 6 minutes without oxygen. After 10 minutes, the damage is usually irreversible. Every second matters. This is why water safety is so important, why drowning is such a terrifying and urgent emergency. There's no time to waste, no time to hesitate. The clock starts the moment someone goes under and doesn't come back up. All of this, the drowning process, the panic, the laryngospasm, the water in the lungs, the hypoxia, is what happens when we try to be something we're not. When we try to stay in an environment our bodies weren't built for. It's a reminder, a harsh one, that for all our adaptability, for all our intelligence and tool-making and ability to shape the world around us, we have limits. Physical limits, biological limits. We can't breathe water. We can't extract oxygen from H2O. We can't survive submerged. These are facts written into the structure of our lungs, the chemistry of our cells, the evolutionary history that made us what we are. So what would it actually take to change that? To make a human capable of breathing underwater? It's a question worth exploring, if only to understand just how deeply our terrestrial nature is embedded in our biology. You couldn't just add gills to a human and call it done. Gills require a completely different respiratory architecture. They need massive surface area, far more than we could pack into a reasonable volume. They need a one-way flow of water, constantly moving across the gas exchange surfaces, which would require restructuring the entire head and neck. They need blood vessels arranged in that countercurrent pattern, flowing opposite to the water, and even if you could somehow engineer all of that, even if you could create functional gills, they still wouldn't provide enough oxygen to keep a warm-blooded mammal alive. Remember, fish are cold-blooded. Their metabolism runs slowly. They don't need as much oxygen per kilogram of body weight as we do. We're warm-blooded. We maintain a constant body temperature of around 98.6 degrees Fahrenheit no matter what the external temperature is, and that takes energy. Lots of it. Our basal metabolic rate, the energy we burn just to stay alive at rest, is many times higher than a fish of equivalent size. We need more oxygen to fuel that metabolism, much more, and water simply doesn't contain enough dissolved oxygen to meet those needs, even with the most efficient gills imaginable. This is why marine mammals, the whales and dolphins and seals that live in the ocean, all breathe air. They're warm-blooded like us. They have high metabolic demands like us, and gills wouldn't cut it. They need lungs. They need to surface. They need access to the atmosphere, where oxygen is abundant. But let's say, hypothetically, that you could somehow solve the oxygen supply problem. Maybe you engineered super efficient gills that could extract enough oxygen from water to support a human metabolism. You'd still have other problems, huge ones. Water is dense, it's heavy. Moving it through gills or any other respiratory structure takes work, muscular effort. The more water you need to process to get enough oxygen, the more energy you spend doing it. And if you're spending energy to breathe, that energy has to come from somewhere, which means you need even more oxygen, which means you need to process even more water, and the whole thing becomes a vicious cycle. At some point, the energy cost of breathing exceeds the energy gained from the oxygen you're extracting, and the system fails. You can't sustain it. Then there's the problem of carbon dioxide. Even if you could get enough oxygen from water, you still need to get rid of carbon dioxide. And carbon dioxide dissolves in water, yes, but the concentration gradients would be different from what our bodies are used to. The pH balance would shift. The whole chemistry of respiration, which has been fine-tuned over hundreds of millions of years to work with air, would need to be recalibrated for water. It's not impossible, obviously, fish do it. But fish evolved, gradually, over immense time spans, developing all the necessary adaptations step by step. Lungs to gills, air breathing to water breathing. You can't just flip a switch and make that transition. It would require changing almost everything about how our respiratory and circulatory systems function. Consider too the physics of pressure underwater. This is something divers understand intimately, but it's worth exploring because it reveals yet another way in which our bodies are fundamentally unsuited for aquatic life. At the surface, we live under 1 atmosphere of pressure, about 14.7 pounds per square inch, the weight of all the air above us pressing down. We don't notice it because we evolved under this pressure, because it's balanced by the air inside our lungs and the gases dissolved in our tissues. But underwater, pressure increases dramatically. For every 10 meters of depth, roughly 33 feet, the pressure increases by 1 atmosphere. At 10 meters, down, you're experiencing 2 atmospheres of pressure. At 20 meters, 3 atmospheres. At 100 meters, 11 atmospheres. And pressure does strange things to gases. If you descend while holding your breath, the air in your lungs compresses. At 10 meters, it's half the volume it was at the surface. At 20 meters, a third. Your lungs shrink. Your chest cavity compresses. If you go deep enough, the pressure can become crushing, literally. squeezing your lungs down until they can't expand anymore, until blood vessels rupture and fluid leaks into the alveolar spaces. This is called lung squeeze, and it's one of the many dangers that freedivers face when they push to extreme depths. The human body can withstand remarkable pressure, it's true. Freedivers have descended past 100 meters, past 200 meters even, on a single breath. But they can only stay there for moments. They have to return quickly before the pressure causes irreparable damage, before their oxygen runs out. And it's not just the lungs. Pressure affects the gases dissolved in your blood and tissues. Nitrogen, which makes up about 78% of the air we breathe, normally doesn't do much. It's inert. Your body doesn't use it. It just comes in with each breath and goes out again. But under pressure, nitrogen behaves differently. At higher pressures, more nitrogen dissolves into your blood, like carbonation dissolving into a soft drink. The deeper you go, the more nitrogen accumulates. And if you come back up too quickly, if the pressure drops too fast, that dissolved nitrogen comes out of solution suddenly, forming bubbles in your blood and tissues. These bubbles can block blood vessels, cause strokes, damage your nervous system, lodge in your joints, and cause excruciating pain. This is decompression sickness, also called the bends, and it's a serious, potentially fatal condition that can affect anyone who ascends from depth too rapidly. Divers manage this by ascending slowly by making decompression stops at specific depths, allowing the nitrogen to leave their bodies gradually safely. But it's a constant concern, a mathematical problem that has to be solved on every dive that goes below a certain depth or lasts longer than a certain time. Your body keeps a ledger of nitrogen, absorbing it under pressure, releasing it during ascent, and if you miscalculate, if you don't give it enough time to equalize, you pay the price. Fish don't have this problem, or at least not to the same degree. Their bodies are adapted to pressure changes. Many deep-sea fish lack swim bladders, the gas-filled organs that would compress or expand dangerously with depth changes. Their bodies are built to withstand pressure that would crush us. They live in a world we can only visit briefly, carefully, with specialized equipment and extensive training. And even with all that equipment, even with scuba tanks and regulators and dive computers and years of experience, human divers are limited. There's a depth beyond which we simply cannot go, no matter what technology we have. Below about 330 meters, roughly 1,000 feet, nitrogen narcosis becomes so severe that divers lose the ability to think clearly, to make rational decisions. They experience a kind of drunkenness, a euphoria that can lead to fatal errors in judgment. Deeper than that, even breathing special gas mixtures designed to minimize nitrogen, the pressure itself becomes directly toxic. High partial pressures of oxygen cause seizures. Helium, often used in deep diving to replace nitrogen, causes high-pressure nervous syndrome at extreme depths, tremors and convulsions that make useful work impossible. The deepest a human has ever dived while breathing compressed gas is about 330 meters. That's the practical limit. Beyond that, we need submersibles, vehicles with walls thick enough to withstand the pressure, machines that keep us in a bubble of normal atmospheric pressure while we descend into the abyss. We can visit the deepest parts of the ocean, the Mariana Trench, nearly 11,000 meters down, but only inside these protective shells. We're observers, not participants. We can't step outside, we can't swim in that water. The pressure would kill us instantly. Our bodies would be crushed, our lungs would collapse. We are utterly, completely alien to that environment, and it to us. This is the ocean we came from, millions of years ago. Our most ancient ancestors, the first vertebrates, swam in these waters, but they were different creatures, adapted to aquatic life in ways we're not. And when some of them began to change, when they started developing lungs and venturing into shallower water and eventually onto land, they set in motion a process that led, eventually, to us, to mammals, to humans. And in doing that, they left the deep ocean behind, not just as a habitat, but as a possibility. Because once you commit to air, once your entire physiology reorganizes itself around extracting oxygen from the atmosphere, going back becomes almost impossible. Look at what happened with marine mammals, the whales and dolphins and seals that returned to the ocean after their ancestors had already adapted to land. These animals descended from terrestrial mammals, creatures with 4 legs that walked on solid ground and breathed air. Somewhere around 50 million years ago, the ancestors of modern whales were land-dwelling animals, possibly something like small hoofed mammals. They started spending more time in the water, hunting fish in coastal areas, gradually becoming more and more aquatic. Over millions of years, their bodies changed. Their front limbs became flippers. Their hind limbs disappeared entirely, absorbed back into the body. Their tails developed flukes. Their nostrils migrated from the front of their snouts to the tops of their heads, becoming blowholes. They became streamlined, torpedo-shaped, perfectly adapted for moving through water. But they kept their lungs. They had to. Because even after 50 million years of evolution, even after all those changes that made them supremely suited to aquatic life, they couldn't evolve gills. They couldn't go back to extracting oxygen from water. Their warm-blooded metabolism, their mammalian heritage, prevented it. So they became creatures of two worlds, living in the ocean but tied forever to the surface, to the air. They have to breathe. Every few minutes, every few hours, depending on the species, they have to come up. They have to expose their blowholes to the atmosphere. They have to exhale and inhale, and then they can dive again, back into the depths, holding their breath like we do when we go underwater, but doing it far better, far longer, because their bodies have evolved incredible adaptations for breath-hold diving. Whales have blood that can carry far more oxygen than ours. Their muscles are packed with myoglobin, storing oxygen in the tissue itself. Their spleens can contract during dives, releasing stored red blood cells into circulation and temporarily boosting their oxygen-carrying capacity. They can slow their heartbeats to a crawl, redirect blood flow to only the most essential organs, tolerate levels of lactic acid buildup that would be toxic to us. They're magnificent diving machines. Sperm whales can stay underwater for 90 minutes or more, diving to depths of 2,000 meters or greater, hunting giant squid in total darkness. Cuvier's beaked whales have been recorded staying submerged for nearly 4 hours, diving to depths of 3,000 meters. These are extraordinary achievements, pushing the limits of what mammalian physiology can do. But they're still holding their breath. They're still depending on the oxygen they took in at the surface. They're still, fundamentally, air breathers, just like us, just like all mammals. It's part of what defines us as a group. And this constraint, this need to breathe air, shapes everything about how marine mammals live. It determines where they can hunt, how long they can search for food, how deep they can go. It makes them vulnerable when they surface, exposing them to predators, to boats, to changes in weather. It forces them to balance the need for oxygen against the need to feed, to socialize, to migrate. It's a limitation, but it's also what they are. They're mammals that return to the ocean but couldn't entirely let go of the air. They're caught between two worlds, just like we are when we swim or dive, though they're far better at managing that balance than we could ever be without technology. But even they can drown. Even whales can die if they can't reach the surface to breathe. Sick whales, injured whales, whales tangled in fishing nets, they drown just as surely as humans do. Their lungs fill with water. Their blood oxygen drops, their brains shut down. The mechanism is the same. The vulnerability is the same. Because lungs are lungs, whether they belong to a human or a whale or a seal or a dolphin. They all work the same way. They all require air, and they all fail in water. This is what it means to be an air breather. It means you're tied to the atmosphere, dependent on it, vulnerable without it. You can adapt to many things. You can live in deserts where water is scarce, in mountains where oxygen is thin, in polar regions where temperatures drop far below freezing. Humans have settled in almost every terrestrial environment on Earth, finding ways to survive and thrive in conditions that would seem impossible. But we can't live underwater. That's the one environment that's closed to us, not because of temperature or pressure or availability of food, but because of something more fundamental. Because we breathe air, and water doesn't have enough of it. It's a simple constraint with profound implications. It defines what we can do and where we can go. It shapes our civilizations, our technologies, our very sense of what's possible. Think about how different human history would be if we could breathe underwater. Our cities would be different. Our trade routes would be different. Our understanding of geography and territory would be completely transformed. The ocean, instead of being a barrier or a highway that requires boats, would be just another space to move through, like land. We'd have underwater settlements, farms, mines. We'd exploit the ocean floor the way we exploit the continents. The three-dimensional nature of aquatic space would change how we think about distance and proximity and ownership. Wars would be fought differently. Cultures would develop differently, everything would be different, because so much of what makes human society what it is comes from the fact that we're terrestrial, that we live on the surface of the land, that the ocean is alien to us, inaccessible except with great effort and technology. But we can't breathe underwater, so none of that alternative history exists. We're land dwellers who happen to be quite good at building boats and submarines and diving equipment. We're clever enough to visit the ocean, to study it, to extract resources from it, to cross it. But we don't live in it. We can't. Our biology won't allow it. And in some ways, maybe that's for the best. Maybe it's good that there's one environment on Earth that remains fundamentally alien to us, one frontier that we can explore but never truly conquer. The ocean keeps its mysteries. It remains wild in a way that land increasingly doesn't. We've mapped its surface, charted its currents, catalogued many of its species, but the depths are still largely unknown, still unexplored, still full of discoveries waiting to be made. And part of what makes those discoveries so remarkable is how difficult they are to achieve, how much effort and technology it takes to reach those depths and see what's there. If we could breathe underwater, if the ocean was as accessible to us as the land, it would be less special somehow, less mysterious. We'd have settled it, exploited it, changed it the way we've changed so much of the terrestrial world. The fact that we can't breathe there, that we can't stay there, preserves something. It keeps the ocean as other, as different, as a realm that operates by rules we don't fully understand and can't fully participate in. And maybe that's valuable. Maybe we need that reminder that we're not masters of everything, that there are places and spaces and ways of being that are beyond us, not because we lack the will or the intelligence to reach them, but because we're simply not built for them. The ocean is vast. It covers 71% of Earth's surface. It's home to an estimated 2 million species, though we've identified only a fraction of them. It produces more than half the oxygen in our atmosphere through the photosynthesis of phytoplankton and other marine plants. It regulates the global climate, absorbing heat and carbon dioxide, driving weather patterns, distributing warmth from the equator to the poles through vast currents. It's essential to life on Earth, including our lives. We depend on it even though we don't live in it, and we always will. The ocean's health is our health. Its fate is tied to ours, and yet we can never truly know it the way we know the land. We can never walk its floor unaided, never feel its water in our lungs and survive, never call it home. We are visitors. We've always been visitors. From the first human who waded into the shallows, to the first diver who held their breath and swam down to see what was below, to the first submersible that descended into the abyss, we've been exploring a world that isn't ours, looking at life that evolved along completely different lines, marveling at adaptations we can never share. And that's okay. That's how it should be. We have the land, we have the air, we have our niche, our place in the ecosystem, our way of being. And the ocean has its own. The two overlap, interact, influence each other, but they're separate, different. And we can't cross that boundary without help, without technology, without acknowledging that we're stepping outside our natural element. So the answer to why we can't breathe underwater remains the same, no matter how many ways we examine it. We're built for air. Our ancestors made that choice, or had it made for them, hundreds of millions of years ago, and every breath we take is a consequence of that ancient divergence. We breathe air because our lungs are built for air. We can't breathe water because our lungs fail in water. It's that simple, and that fundamental, and that unchangeable, at least within the bounds of what we are as a species. We are Homo sapiens, we are mammals, we are terrestrial vertebrates with lungs and warm blood, and a metabolism that demands more oxygen than water can easily provide. These facts define us, they shape us, they limit us, but they also make us what we are. Without air, without lungs adapted to extract oxygen from the atmosphere, we wouldn't exist. Not as humans, not as anything recognizable. The water is still there, the ocean is still vast, and we're still here, breathing air, unable to do anything else, carrying the story of that ancient transition in our bodies, and remembering, in the deep structure of our cells and organs, where we came from and why we left. There's no going back. Not really, not without losing everything that makes us what we are. But there's a kind of peace in that, in knowing your place, in understanding your limits, in breathing easily, naturally, the way you were designed to breathe, and being grateful for air that asks nothing of you except that you breathe it. Because it's enough. It always has been. And for as long as humans have existed, for as long as they will exist, air will be enough. The ocean can keep its mysteries. We have the sky. We have the atmosphere. We have oxygen flowing free and abundant, waiting to be breathed, waiting to sustain us every moment of every day, for every generation that comes after, just as it sustained every generation that came before. And even if you could make all those changes, even if you could bioengineer a human capable of extracting oxygen from water, you'd be creating something that wasn't quite human anymore. Not in the biological sense. You'd be creating a new species, something adapted to an aquatic environment in ways that would fundamentally alter its physiology, its metabolism, perhaps even its nervous system and brain structure. It's a fascinating thought experiment, the stuff of science fiction and speculative biology. But it's not a practical solution to the question of breathing underwater. The reality is simpler and starker. We can't breathe underwater because we're not built for it. Our ancestors chose air, they chose land, and we inherited that choice. Every part of us, from our lungs to our metabolism to the chemoreceptors in our brainstem that tell us when to breathe, is optimized for life in the atmosphere. Changing that would mean changing what we are at the most fundamental level. There's something humbling about that realization. We've accomplished extraordinary things as a species. We've built cities, invented technologies, explored space, cured diseases, reshaped entire ecosystems. We're capable of feats that would seem like magic to our ancestors, but we can't breathe underwater. That simple limitation, that one physical constraint, is beyond us. Not because we lack the intelligence to solve it, but because solving it would require rewriting biology itself. And biology doesn't rewrite easily. It's conservative. It's built on structures and systems that have been tested and refined over millions of years. You can modify them, tweak them, adapt them to new purposes. Evolution does that all the time. But wholesale, replacement, complete redesign, takes time. Geological time. Millions of years. We don't have that. We have the bodies we evolved to have, built for the environment we evolved in, and the ocean, for all its importance in our history, for all that it shaped us and gave rise to our distant ancestors, is no longer our home, yet we remain connected to it. Not just through evolutionary history, not just through the diving reflex or the salt in our blood, but through a deeper, harder to articulate bond. Water sustains us. We drink it. We bathe in it. Our crops need it. Our cities are built near it. More than half of the oxygen we breathe comes from the ocean, produced by phytoplankton drifting in the sunlit upper layers. The ocean regulates our climate, drives our weather patterns, feeds billions of people. We depend on it utterly, even though we can't live in it. And perhaps that's fitting. Perhaps it's right that we should be visitors to the ocean, guests rather than residents. We can appreciate it, study it, marvel at its depths and its mysteries, without needing to reclaim it as our habitat. The question we started with, why can't we breathe underwater, has led us through chemistry and physics, through evolutionary history and physiological mechanisms, through the structure of lungs and gills, through the diving reflex and the drowning process and the limits of human adaptation. And the answer, ultimately, is that we're land animals. We're air breathers. We have lungs designed for extracting oxygen from the atmosphere, chemoreceptors tuned to detect carbon dioxide in our blood, metabolisms that demand more oxygen than water can provide, bodies that panic and fight when submerged. Every part of us says no to the water as a place to breathe. We can hold our breath, we can dive, we can swim, but we cannot stay. We cannot live there. We have to come back. Back to the surface, back to the air, back to the world we were made for. And maybe that's the real lesson. Not just that we can't breathe underwater, but that we're not supposed to. We're built for something different. For walking on solid ground, for breathing the open sky, for a world where the air is free and the oxygen abundant. That's our niche. That's what evolution shaped us for. And it's enough. More than enough. Because in choosing air over water, in developing lungs instead of keeping gills, our ancestors didn't lose something. They gained a whole world, the terrestrial world. A world of forests and plains, mountains and deserts, rivers and lakes. A world where they could move quickly, see clearly, communicate through sound, use their hands to manipulate objects, and eventually to create tools. A world where they could build fires, which require oxygen from the air to burn. A world where civilization became possible. If we could breathe underwater, if we'd stayed aquatic, we'd be different creatures living different lives. We might have our own civilizations, our own technologies, but they wouldn't look anything like what we have now. You can't forge metal underwater, you can't make fire, you can't easily manipulate complex tools without a solid surface to brace against. The ocean is magnificent, but it's also limiting in ways that land is not. By leaving it, by adapting to air, our ancestors unlocked possibilities that would have been impossible in the depths, and we're living in the world those possibilities created. Every breath we take is a reminder of that choice, that transition, that moment in deep time when our ancestors crawled up onto the beach and decided to stay. So tonight, as your thoughts drift and your breathing slows into the rhythm of approaching sleep, consider the air moving in and out of your lungs. Feel it, if you can, the gentle expansion of your rib cage, the soft pressure of your diaphragm moving down and back up again, the whisper of air through your nose or mouth. You're breathing without thinking about it the way you've been, breathing since the moment you were born, the way humans have been breathing for hundreds of thousands of years, and before humans, the way our mammalian ancestors breathed for millions of years, and before them, the way the first tetrapods breathed when they emerged onto land 400 million years ago. This rhythm, this exchange of gases, this dance between oxygen and carbon dioxide is ancient. It's part of our inheritance, part of what makes us what we are. The ocean is still out there, vast and deep, covering most of our planet, teeming with life that breathes water the way we breathe air. Fish gliding through the depths, pulling oxygen from every mouthful of water that flows past their gills. Whales rising to the surface to breathe, their blowholes misting the air with moisture from their lungs before they dive again into the silent blue. Dolphins racing through the waves, surfacing and diving in an endless rhythm. All of them adapted to the water in their own ways. All of them solving the problem of how to get oxygen in an environment where oxygen is precious and hard to extract. They're not struggling. They're not suffering. They're exactly where they're supposed to be, doing exactly what they evolved to do. Just as we are. Just as you are, lying here, breathing easily, safely surrounded by air. We can't breathe underwater. We never could. We never will, not without technology, not without changing what we are so fundamentally that we'd no longer be human. But we don't need to. We have the air. We have the atmosphere. We have a whole world built for creatures like us, creatures with lungs and warm blood, and bodies designed to walk upright under an open sky. And that world, that air, has been enough for our entire history as a species. It sustained our ancestors as they spread across the continents. It sustained the first humans as they discovered fire and art and language. It sustains you now in this quiet moment as oxygen flows into your blood and carbon dioxide flows out as your cells burn fuel and produce energy, as your brain processes these words and your body rests and prepares for sleep. The water is beautiful. The ocean is essential. We're connected to it in ways we sometimes forget, in ways written into our biology and our history. But it's not our home, not anymore. We left it behind millions of years ago in favour of land and air, and in doing so, we became something new, something different, something that can look at the ocean from the shore and appreciate its vastness and its mystery without needing to reclaim it. We're visitors to the water now, brief guests. We can wade in its shallows, we can swim on its surface, we can hold our breath and dive beneath, stealing moments in that alien world. But we always come back. We have to. The air calls to us. The need to breathe calls to us. And we answer. We surface. We gasp. We fill our lungs with the atmosphere that has sustained our lineage for longer than we can truly comprehend. This is what we are. Air breathers, land dwellers, mammals whose lungs demand oxygen from the air and whose bodies reject the water that would flood those lungs and stop that breathing. We're shaped by that reality every moment of every day, even when we're not thinking about it, even when we're simply existing, living our lives, breathing in and breathing out. The question was simple: why can't we breathe underwater? And the answer, when you trace it through all the layers of biology and chemistry and physics and evolutionary history, comes down to this. Because we're built for something else. Because our ancestors made a choice, or had a choice made for them by the forces of natural selection, and that choice sent us down a path that led away from the water and onto the land. And every breath you take, every easy inhalation of oxygen-rich air is the continuation of that ancient story. The echo of that choice made in deep time by creatures who looked nothing like you, but whose lungs and hearts and metabolisms are still recognizable in yours. We can't breathe underwater, but we can breathe air, easily and endlessly, as long as we stay where we belong. And that's more than enough. It's everything. It's life itself, measured out in breaths, in the constant exchange between the air around us and the blood within us. The ocean will keep its mysteries. It will keep its depths and its creatures and its ways of being that are foreign to us. And we will keep the air, we will keep the sky, we will keep breathing the way our ancestors breathed, the way our descendants will breathe, the way every human who has ever lived has drawn breath after breath after breath, from the first gasp to the last. This is our inheritance. This is what we are. And it's written into every cell, every tissue, every organ, especially the lungs, those remarkable structures that evolved hundreds of millions of years ago to pull oxygen from air and have been doing that. Same job in countless species across immeasurable time down to this moment, this breath, this quiet exchange of gases that keeps you alive. So rest easy, breathe deeply, let the air fill your lungs and let it go again, over and over, in the rhythm your body knows without being taught. You don't need the water, you have everything you need right here, in the air that surrounds you, invisible but essential, always present, always enough. The ocean is vast and we are small, but we have our place, we have our element, we have air. And as long as we keep breathing it, as long as our lungs keep expanding and contracting, and our blood keeps flowing and our hearts keep beating, we have life. Simple, straightforward, terrestrial life. The life we were made for. The life our ancestors fought to protect when they crawled out of the ancient seas. The life we inherit, breath by breath, moment by moment, for as long as we're here. The water is still there, the ocean is still vast, and we're still here, breathing air, unable to do anything else, carrying the story of that ancient transition in our bodies, and remembering, in the deep structure of our cells and organs, where we came from and why we left. There's no going back. Not really. Not without losing everything that makes us what we are. But there's a kind of peace in that. In knowing your place, in understanding your limits, in breathing easily, naturally, the way you were designed to breathe, and being grateful for air that asks nothing of you except that you breathe it. Because it's enough. It always has been. And for as long as humans have existed, for as long as they will exist, air will be enough. The ocean can keep its mysteries. We have the sky. We have the atmosphere. We have oxygen flowing free and abundant, waiting to be breathed, waiting to sustain us, every moment of every day, for every generation that comes after, just as it sustained every generation that came before. And there's something profound about breathing itself, beyond just the mechanics of gas exchange, beyond the physics and chemistry we've explored. Breathing is the rhythm of life. It's the one thing you've done continuously since the moment you were born, the one thing you'll keep doing until the moment you die. Your heart beats without your conscious control, yes, but breathing occupies a unique space. It's automatic, controlled by your brainstem, happening whether you think about it or not. But it's also voluntary. You can hold your breath. You can breathe faster or slower. You can control it in ways you can't control your heartbeat, or your digestion, or any other autonomic function. This dual nature, this bridge between conscious and unconscious, makes breathing special. In many meditation traditions, breathing is the anchor, the thing you return your attention to when your mind wanders. Why? Because it's always there, always accessible, always moving in that steady rhythm, in and out, rise and fall, watching. Your breath, feeling it, following it, brings you into the present moment in a way few other things can. It connects you to your body, to your aliveness, to the basic fact of your existence. You are breathing, therefore you are. It's more immediate than thought, more fundamental than emotion. It's the substrate of consciousness itself. When you're anxious, your breathing becomes shallow and rapid. When you're calm, it deepens and slows. The relationship goes both ways. Your mental state affects your breathing, but your breathing also affects your mental state. Slow, deep breaths activate your parasympathetic nervous system, the rest and digest response, lowering your heart rate, reducing stress hormones, calming your mind. This connection between breath and mind, between oxygen and consciousness, is something we rarely think about. But it's profound. Your brain, that 3-pound organ that generates all your thoughts and feelings and perceptions and memories, is incredibly hungry for oxygen. It represents only about 2% of your body weight, but it consumes roughly 20% of the oxygen you breathe. 20%. That's an enormous proportion. Your brain can't store oxygen. It can't stockpile it for later use. It needs a constant, uninterrupted supply, delivered by blood that flows through hundreds of miles of capillaries, reaching every neuron, every synapse, every cluster of cells that fires and creates the phenomenon we call mind. When oxygen delivery to your brain is interrupted, even for seconds, you start to lose consciousness. Within 4 to 6 minutes without oxygen, brain cells begin to die. The damage becomes irreversible. This fragility, this absolute dependence on continuous oxygen delivery, shapes everything about how we experience the world. You can't hold your breath indefinitely. You can't decide to stop breathing and maintain consciousness. Your body won't let you. The rising carbon dioxide triggers an irresistible urge to breathe that overrides your conscious will. It's a safety mechanism, a biological override that ensures your brain gets the oxygen it needs to survive. And it's part of why being underwater, being in an environment where you can't breathe, is so fundamentally threatening. It's not just physically dangerous, it's existentially terrifying, because it threatens the very basis of consciousness. Think about what we've gained by breathing air. By having access to abundant oxygen, we've gained the ability to sustain complex thought, sophisticated language, abstract reasoning, creativity. The human brain, with its billions of neurons and trillions of connections, its capacity for self-reflection and imagination and planning, requires enormous amounts of energy to operate, and that energy comes from oxygen. Every thought you think, every memory you form, every decision you make, depends on oxygen flowing into your brain and fueling the chemical reactions that make neurons fire. Without the abundant oxygen in air, without lungs efficient enough to extract it and blood capable of carrying it, we couldn't have evolved the brains we have. We couldn't have become human in the recognizable sense. This is part of what our ancestors gained when they left the water. Not just the ability to walk on land, not just access to new food sources and new habitats, but the metabolic foundation for intelligence. Warm-blooded metabolism, made possible by efficient lungs breathing oxygen-rich air, enabled larger brains. Larger brains enabled more complex behaviors, better memory, improved learning, social cooperation. These advantages built on each other, creating a feedback loop that eventually led to language, to culture, to technology, to everything that makes human civilization possible. And all of it rests on that foundation of breathing air, of having lungs that work reliably and efficiently, extracting oxygen from the atmosphere and delivering it to cells that need it. We are what we breathe, quite literally. The air we breathe shapes the thoughts we think, and we share this gift with every air-breathing animal. Every mammal, every bird, every reptile, every amphibian in its adult form breathes air the same basic way we do. Lungs expand, air rushes in, oxygen diffuses across membranes into blood, carbon dioxide diffuses out. The details vary. Bird lungs work differently from mammal lungs, with a one-way flow system that's remarkably efficient. Reptile lungs are simpler, less subdivided than ours, but the principle is the same. Air breathing unites us. It's a shared inheritance from our common ancestors, those first tetrapods that crawled onto land 400 million years ago. When you see a bird flying overhead, a dog walking beside you, a lizard sunning itself on a rock, you're seeing fellow air breathers, creatures whose lungs, different as they may be from yours, are doing the same job, taking oxygen from the atmosphere and using it to power life. There's a kinship in that, a connection that crosses species boundaries. We're all dependent on the same resource, the same element, the same simple molecule of two oxygen atoms bonded together. We all need it, we all breathe it, and we all suffer without it. The bird and the dog and the lizard and you all tied together by this basic need, this fundamental requirement that shapes how we live and where we can go and what we can do. The ocean is closed to all of us. We're land creatures, air creatures, united in our dependence on the atmosphere. And in a world where so much divides species from each other, where predator and prey, where competition and conflict are constant, there's something strangely comforting about this shared vulnerability. We all need to breathe. None of us can do it underwater. We're all in this together, in the most literal sense. The ocean, meanwhile, belongs to different kinds of life. Life that solved the oxygen problem differently, fish that extract dissolved oxygen from water with their gills, jellyfish that absorb oxygen directly through their body surfaces, octopuses with blue copper-based blood instead of red iron-based blood, adapted to the lower oxygen levels in seawater, marine invertebrates with body plans so different from ours that comparing them feels like comparing life from different planets. The ocean is alien to us not because it's on Earth, not because we evolved from aquatic ancestors, but because it operates by different rules now. We've diverged. Air breathers and water breathers, separated by hundreds of millions of years of evolution, by fundamentally incompatible respiratory systems, by environments that might as well be different worlds. And yet, we're still connected. The oxygen we breathe comes partly from the ocean. Phytoplankton, tiny photosynthetic organisms drifting in the sunlit surface waters, produce enormous amounts of oxygen as a byproduct of photosynthesis. Some estimates suggest that marine photosynthesis produces 50 to 80% of the oxygen in Earth's atmosphere. The ocean, which we can't breathe, produces the air we do breathe. It's a beautiful irony. A reminder that ecosystems are interconnected, that the ocean and the atmosphere are not separate but parts of a single system, exchanging gases, nutrients, energy. The health of the ocean affects the air we breathe. The composition of the atmosphere affects ocean chemistry. We're all part of the same planetary system, even if we occupy different niches within it. So when we ask why we can't breathe underwater, when we trace all the reasons through biology and physics and chemistry and evolution, we're really asking about our place in that system, about what we are and what we're not, about the choices evolution made, or that were forced upon it by circumstances, that led to us being air breathers instead of water breathers. And the answer, complex as it is, ultimately comes down to this. We breathe air because our ancestors did. Because 400 million years ago, some fish developed lungs and started gulping air from the surface. Because those lungs turned out to be advantageous, allowing survival in oxygen-poor water, enabling eventually the move onto land. Because once the transition to terrestrial life began, there was no going back. Because warm-blooded metabolism and complex brains and the whole trajectory that led to humans depended on abundant oxygen from air. Because we are what we are, built the way we're built, limited and enabled by our evolutionary history. We can't breathe underwater because we're not fish. We're mammals. We're primates. We're humans. And every level of that classification, every step in that hierarchy of life, is defined partly by how we breathe. Mammals have lungs and breathe air. Primates have lungs and breathe air. Humans have lungs and breathe air. It's part of our identity, part of what we are at the most basic level. Change that. Make it possible for humans to breathe water, and you'd be changing something so fundamental that the result wouldn't really be human anymore. It would be something new, something different, something adapted to an environment we're not adapted to, with a biology we don't have, with limitations and capabilities that we can't fully imagine. And maybe that's okay. Maybe it's fine that there are limits to human adaptability, that there are environments we can't inhabit, challenges we can't overcome with biology alone, only with technology. It keeps us humble. It reminds us that for all our achievements, for all our cleverness and innovation and ability to reshape the world, we're still just animals, still bound by the same physical and chemical laws that govern all life, still dependent on oxygen and water and food and a relatively narrow range of environmental conditions. We've accomplished remarkable things, yes. We've built civilizations, explored space, cured diseases, created art and music and literature. But we can't breathe underwater. That simple fact, that basic limitation, is a reminder that we're part of nature, not separate from it. Subject to its laws, shaped by its forces, products of a history that stretches back billions of years and includes countless other species, most of which are now extinct. So rest now. Let your breathing slow and deepen. Feel the air moving in and out, cool as it enters, warm as it leaves. Feel your chest rise and fall, your diaphragm contract and relax, the ancient rhythm that has sustained life on land for hundreds of millions of years. You're part of that story. Part of that unbroken chain of breaths that stretches from the first lungfish gasping at the surface to you. Here, now, breathing without effort or thought. The ocean is out there, The water is still vast, but you're here, safe, surrounded by air, breathing the element you were made to breathe, living the life you were made to live. And that's enough. It's more than enough. It's everything you need. The question was simple: why can't we breathe underwater? And the answer, traced through all its layers, brings us back to this moment, this breath, this simple fact of being alive and breathing, and exactly where we're supposed to be. Not in the water. Here, breathing air, being human. And that's exactly right.